Alright, so welcome to another video. So far what we have done is we have fetched the data using Y-Finance. We've fetched the macroeconomic data. We created the pre-processing function. We have created new features for our data. Then we talked about the baseline models, the ARIMA, the autoregressive model, and the simple linear regression model. We create a function to evaluate those models. We're going to be using the same functions to evaluate the deep learning model as well. Mentioning deep learning model, this video is going to be about building a deep learning model. I'm going to be talking about what layers I have used. I'll be explaining briefly about each of those layers, and I'll tell you why I have chosen those layers, what goes into my mind when I'm experimenting with different layers. So first of all, before I go on to talk about those layers, let's just create a function for our deep learning LSTM model. So then I'll explain about each of those layers there. So def build LSTM model. We're gonna be inputting input shape. I'll explain what this shape is. It is basically the we'll be passing out the data in certain shape that goes into the first layer of our deep learning model. So that's what this input shape is. And print, I'll just want to make sure that input shape is as desirable that I have thought of. I'll explain about that in future when we'll be training our model with this function, but I'm just going to be printing the input shape. And that helps in the debugging as well if something goes wrong. Anyway, inputs are going to be input. Shape is input shape is the first element of input shape, and the second element of input shape. So that's gonna be the input of our deep learning model. The first layer of our deep learning model is gonna be LSTM out, the output of the LSTM, and we're going to be using something called bidirectional LSTM. I'm going to be explaining each of those terms in detail once we are finished with this coding. So bidirectional LSTM, the 64 units of those. I do want to return sequence, so return sequence is going to be true. Then I do want to have a dropout as well, just to avoid the overfitting. So that's going to be a 30% of dropout, and also recurrent dropout. It's going to be 0.2, just about 20% there. Sorry, something's bothering me at my nose. Anyway, the second layer is going to be attention layer. Again, I'm going to be explaining what attention layer is and why we have used this attention, and that's going to be LSTM out, LSTM out. The third layer again is going to be LSTM. It's going to be a simple LSTM, not without bidirectional. So LSTM with 32 units this time, and do not want to return these sequences, and I do still want to have some sort of dropout there. So the sequence is going to be false. Dropout is going to be different than that. 30% is probably 20%. Recurrent dropout is going to stay the same, and I'm going to pass in attention. Then we're gonna have a batch normalization. LSTM out, and then we will have layers for fully connected layers for dense layers with the dropout. So dense out is going to be the first layer of dense is of 32 units, and the activation function is going to be relu. And I'll pass in LSTM out. Then we have dropout, just to avoid the overfitting again, and that's going to be 30%. I have kept it there, and I'll pass the first layer there, dense out, and the another dense layer is going to be of 16 units, with again the relu activation function. Just going to be copying it here, and instead of LSTM out is going to be the second layer of the dropout dense out. And then we'll have output of the deep learning network is going to be again a dense layer of 1 unit, which is going to be an output layer. So I'll pass in dense out. Then the model is going to be about model inputs equals to, we have defined inputs, and outputs is going to be equal to output model dot compile, and we're gonna use optimizer Adam. So that is in TensorFlow dot Keras dot optimizer dot Adam, and the learning rate is gonna be 0.001. I started with 0.01 and then went on to keep 0.001, but rate is gonna be equal to 0.001. You need to adjust it in every training phase, whichever is efficient enough. You're gonna be keeping that learning rate. The last function is gonna be MSE, mean squared error, and eventually we'll return model. So let me explain what we have done here, because it's a lot to take in. Sorry, I forgot that comma there. Anyway, so why we have bidirectional LSTM? First of all, what is LSTM? So LSTM is basically a long short-term memory unit, which is a special kind of recurrent neural network cell that is designed to remember the information over many timestamps. Remember, we are dealing with time series data, so we need to, instead of have one timestamp in the memory, we need to have more than one. So that's what LSTM does. It uses 3 gates: input, output, and forget, and it uses those with the combination to control how much of the past data we want to keep in the memory, how much new information we want to write, and what to expose to the next hidden layer of our deep learning model, right? And it's the gating architecture it solves a problem which is vanishing gradient, because what vanishing gradient problem is basically is when we are training the layer of a deep learning model becomes so large that it's almost impossible to handle for the GPU or CPU, so it goes out of the hand. That's the simplest explanation. It's not exactly what it is, but just to make it simple, that is the vanishing gradient. The gradient becomes too large to process, and to solve those vanishing gradient problem that happen in the traditional recurrent neural networks, LSTM was invented, and it deals with that vanishing gradient problems very efficiently. So that's why we are using LSTM. It's really good with the sequential data that we have, time series data. And why we are doing bidirectional then. So a standard LSTM is basically only reads the sequence forward. It reads the next timestamp of the data from t equals to 0 to t equals to t, right? But the financial patterns often requires to have the context of both direction of the past data and of the future data as well, to decide the future predictions, right? So a bidirectional LSTM basically runs two LSTM in parallel. One goes forward and one goes backward in the data, and the output basically are the concatenated. So the each timestamp's representations know what happens before and after that timestamp. That's why we have used bidirectional LSTM. And yeah, so the rationale behind that was to have more context and richer feature extraction, and with that potentially to have better prediction power. So why do we have attention layer? What is attention basically? So let's talk about that. So attention basically, it learns the set of weights. The bidirectional has given us the output. So attention learns the set of weights for each timestamp, effectively asking um, um, which past moments are more relevant to predict the future predictions, make the final prediction of the next timestamp. What are the past data that are most valued to make the prediction? That's what attention layer does basically. It computes the alignment scores between all the pairs of hidden states and normalizes them to the probabilities to take a weighted sum. And why is being used here is because a bidirectional LSTM is already giving us the sequence of hidden vectors, but not every day in the 20-day window. Thinking like this, right? The bidirectional LSTM gives us the sequence, but not every day in 20-day window, and that matters equally. Maybe a sudden drop of 5 days ago is far more predictive than a small change that occurred yesterday. So that's why the attention layer lets the model automatically learn those of important timestamp that has more prediction values rather than and what timestamp doesn't have that much of a power to predict those, and it improves the ability to summarize the sequences into a single vector. And the rationale behind using this attention is just to have adaptive weighting of time steps and have a sharper and more informative summary of the entire sequence of the time series data. And then we have something called, then we have another LSTM layer, and then we have a batch normalization. So batch normalization basically, it rescales the inputs to have a zero mean and unit variance within each mini batch during the training, and it introduces the two learnable parameters, scale and the shift, so the network can still undo the normalization if it has done it, if it is needed during the training process. And why we have used it on the LSTM output layer, why we have passed LSTM output to batch normalization, is basically the second LSTM. It collapses our sequence to a single vector, and these values can have heavily, have widely different ranges, making it the downstreams the training, making downstream training a bit unstable because we have different values falling all over the places, right? By normalizing this, by applying batch normalization on those LSTM out, we're doing three things. We are speeding up the convergence. What convergence is to have achieved the optimal train model having the smoother gradient. The second thing is to reduce the sensitivity to weight initialization, and the third thing is to provide a slight regularization by adding the noise from these batch statistics. The rationale is basically to stabilize and accelerate the learning process on the dense layers that we have after those LSTM layers. Let's talk about those dense layers now. So dense is the basic neuron layer of any deep learning model. So a dense layer it basically multiplies the input vector by weight matrix, and it adds some sort of a bias and applies the non-linearity. Because we have used the activation function ReLU, I'm going to be creating a new video on those of activation functions. But yeah, it lets the model learn the arbitrary non-linear combinations of feature that are extracted by the LSTM and attention blocks. Why have we used two dense layers at all? We could have used just one. Two dense layers. The first layer basically expands the 32-dimension LSTM output to create more richer feature interactions. The second dense layer with the 16 unit is distills those interactions down further before the final regression happens at the model training part. And why we have used dropout? Because we've been using dropout in LSTM, so why we have used here? So dropout basically randomly zeroes out the fraction of the neuron's output that each training step would have, and it prevents basically something called overfitting. When what overfitting is basically when the model learns the training data so perfectly that will fit the training data, but it will not be able to generalize to the new data in the test data, or perhaps the new data that we input, and it will not be that accurate. It will have huge gap between the actual and the predicted value. It predicts the training data perfectly, but is not capable of generalizing over the new data. That's overfitting. The simple rationale behind using the dense layer is to learn the final feature transformations, and the dropout is to just guard against this overfitting problem. And at the end, we are just having another dense layer with one unit to have an output. We are compiling the model with Adam optimization with the loss function of mean squared error, and we are returning the model. So together, these components, these different layers like bidirectional LSTM attention, batch normalization, and dense and dropout layers, it gives us a balanced architecture that captures the temporal patterns and that focuses on the most relevant signals, stabilizing the training process, and it avoids the overfitting of the model as well. So each layer has a clear defined role here, and it's tuning the sizes and layer is the key. I did have when I had this final architectured model, I did have two dense layer before dropout and two after. Then I experimented without dropout. I didn't have batch normalization. I didn't have bidirectional from when I started. I just had normal LSTM. I didn't have attention as well. But experimentation is the key when you are working with the deep learning model, when you are architecting a deep learning model from scratch. Experimentation is the key. Try out different sort of architecture, see what works great with the data that you have at hand. So this architecture, having bidirectional and dropout and batch normalization and attention, worked great with the data that I have at hand. In future, if I decide to include some more data, like if I want to do sentiment analysis on the news articles that happens that they are related to those stock market ticker that I'm working with. In this case, we have used Apple, I believe. Yeah, so if I want to fetch Apple related news articles, and do sentiment analysis and give it a score, and I want to include those data in this one, it will have its own features. Then I'll have to change the architecture of the deep learning model. I'll have to experiment with the new layers, perhaps will reduce the architecture, make it less um, complex, make it more complex. We'll have to experiment, and eventually we'll have a perfect model for that data. So yeah, that was it about building LSTM model. In the next video, we're going to be talking about, backtesting strategies, and eventually we'll be ingesting data that we have to these three different models, and we'll train those models and see how the evaluation works and which model performs better than the other ones. So yeah, that's it for this video. I'll see you guys in the next one.